Okay, sir.
Today you have a lab also, right? After that class?
Yeah, we have 2 class.
Okay, 2 class. That's why I'm taking one class instead of
Yeah, yeah.
late.
We take theory class today, sir.
Yeah, 3 class. Okay. Okay, so so we'll start the chapter 1, which is from the book Simon Ramo, from the book of Simon Ramo, the ideal transmission line. The ideal transmission line chapters. So first of all, we need to know what is the transmission line. See, transmission line is a, what is this? See this? A transmission line maybe made of parallel wires. It is a parallel wires, parallel plates of coaxial conductors, or in general of any two conductors separated by a dielectric material. Any two conductors separated by a dielectric material. Okay. That is the definition of that is the transmission line. Okay, so if I ask you, can you give me some examples of transmission line? Then you can say this, that these are the transmission lines. These are the transmission lines. So parallel wires, parallel plates of coaxial conductors, or in general any two conductors separated by a dielectric material. This is the transmission line. These are the transmission lines. Okay. So first of all, let's take a look. Rotate this one. So let's consider a transmission line, two parallel wires, and we are taking a small distance, dz. We are taking a small distance dz of the transmission line, and this is the equivalent circuit of the transmission lines, parallel wire, two parallel wires. Okay. We are taking the dz distance of the transmission line. Here they have said that consider a differential length of line dz, including only the distributed impedance L per unit length and the distributed capacity C per unit length. The length dz has the inductance L dz and the capacitance C dz. Okay. Now see the voltage drop or the negative charge. See, what would be the voltage drop? Look at the figure here carefully. So instead of this one, we can write this equivalent circuit. That is the equivalent. It's the equivalent circuit. Okay, that is the equivalent circuit. Now, equivalent of parallel this transmission line, parallel wire. Now see voltage drop. Here voltage is V. After passing the distance dz or length dz, then the voltage changes to this one. And here the current L dz. Sorry, here the current I, which changes to this one. I plus del I del z dz. So, what is the voltage change and what is the current change? We have to consider. the voltage drop or negative change in voltage across the length is then equal to the product. So see, here the voltage change is this one. If you look carefully, that is actually voltage change, right? That is actually voltage change. Del V by del Z into dz. This voltage change is equal to minus L dz into del I by del T. Minus L dz into del I by del T. The voltage drop or the negative change in the voltage across the length is equal to the product of this inductance, the time rate of change of current. Product of this inductance minus L dz, the time rate of change of the current. And for such a differential length, the voltage change along it at any instant may be written as the length multiplied by the rate of change of voltage with respect to the length. Then we can write like this: minus L dz into del I by del T. That is the T. Okay. So that is the voltage change actually. Similarly, so one question there, right? Why we are writing here the partial derivatives? Since the reference point may be changed in space of time in completely independent fashion. See, since the reference point may change in space or time. Reference point may change in space or time. It is not fixed. That's why we are using the partial derivative. Which are the partial derivatives? This del, not delta. This del is the partial derivative, right? Because the reference point is not fixed, it will change in time. Okay. Now, what would be the current change? Similarly, look at here. That is the current change. Delta I by delta Z into dz. That is the current change. And that is the negative C dz delta V by delta. The decrease in current across the element at an instant is merely the current that is shunted across the distributed capacity. The rate of decreases of current with distance is given by the capacity multiplied by the time rate of change of voltage. Partial derivatives are again called for. So see, here is the current change. For the voltage change, it is L dz. For the current change, it is C dz and delta V by delta T. Now, just look at here those two equations together. Delta V by delta Z is equal to minus L delta I by delta T. And delta I by delta Z is equal to minus C delta V by delta C. See, that is, these two equations are there. And these two equations, how it comes, just you can consider that dz. If you consider the dz, then it becomes like this. Okay. So these two equations, 3 and 4, these are the fundamental differential equations for the analysis of the ideal transmission line. So these two equations, equation 3 and equation 4, are known as the fundamental differential equations for the analysis of the ideal transmission line, and they are also known as the telegraphist equation. These two equations are also known as the telegraphist equation. Okay. So these two equations are known as the telegraphic equation, and these are the fundamental differential equations for the analysis of the ideal transmission line. Okay, so equation number 3 and 4 are the fundamental differential equations for the ideal transmission line. Okay, now we'll do some calculations. Let's look at it. If we differentiate this one, first one with respect to time and second one with respect to distance, or the first one with respect to distance or second one with respect to time. Let's see. Differentiate 3 partially with respect to distance. First one with respect to distance. Second one with respect to time. Then what will happen? First one, if we differentiate first one with respect to time, then it would be, let me show you what we are doing. We are differentiating respect to distance. Delta by delta set, and this one with respect to time. This one with respect to time. Okay, you got it? I think you got it, right? Now, after that, we will do what? Let's see. After doing the differentiation, you get this delta square v by delta z square is equal to minus L del square I del z del t, and del square I divided by del t del z is equal to minus C del square v by del t square. So you get these two equations. Now look at here very carefully. Look at here. This one, instead of this one, we can write this one. Because look at here, these two are same. Just instead of this, you can write this. So it would be LC delta square V by delta T square. So that is the first equation. Similarly, we can get the I. For I, what we have to do? For the I, we need to do one thing, that is we have to differentiate first one, equation number 3 with respect to time, and equation number 4 with respect to distance. Let me show you. show you that one. Because that is not given here. So if I differentiate with respect to time, then what we get? Del square v del z del t, right? And minus L del square I del t square with respect to time, and this one with respect to distance. Del square I del t square. Second one with respect to distance. First one with respect to time. Minus c del square v del z del t. Okay. Now say, now instead of this one, oh, here is the c. Now instead of this one, instead of this, use another color. Instead of this, you can write this. Okay. So then it would be LC del square I del t square. Is this one. That's how you can do this. Okay, so these equation 7 and 8, these two equations are known as the one-dimensional wave equation. These are known as the one-dimensional wave equation. Okay. Okay. So 7 or 8, these equations are known as the one-dimensional wave equations. Okay. Now let's start another one. Reflection and transmission at discontinuity. Reflection and transmission at discontinuity. Let's look at here another one. Okay, that is the load. Let's see. This is the transmission line. Okay, input, that is the source. This is the source. That is the source. That is Z dot. Source Z dot. Z dot is the impedance of this one, this line. And this Z dot is known as the characteristics impedance. Okay, this Z dot is known as characteristics impedance, right? This is known as the characteristics impedance. Z dot. And this is the source and this is the load. So what happened? See here. Whenever you turn it on, you turned on the source, then it will provide the microwave. Few microwave signals will pass through the load. But few would return. Those are going there, that is B plus. Those are coming, that is B minus. B plus and B minus, and those are here, right? So the loss, how much signal coming from here, that is called the VSWR. But let me show you another thing, that is the transmission reflection coefficient. Reflection coefficient or rho, reflection coefficient rho, which is equal to B minus over B plus. And transmission coefficient, which is tau, that is equal to BL by V plus. See, this is incident wave. V plus is the incident wave, that is incident wave. That is incident wave. V minus, that is reflected. That is reflected. And that is transmitted. So three kind of waves are there. Okay. So V minus is the reflected wave, V plus is the incident wave, and what is the reflection coefficient? Reflection coefficient is the ratio of the reflected wave to the incident wave. And what is the transmission coefficient? That is the ratio of the transmitted wave to the incident wave. And see, VL here is equal to V plus plus BMS. Similarly, IL load voltage is equal to V plus BMS. Similarly, IL is equal to I plus I minus. Plus I minus. Now, let's look at here. So that is the reflection coefficient V plus. And what is the equation of the reflection coefficient? It comes from here. See, you can memorize this one. V minus is equal to RL minus Z naught divided by RL plus Z naught. Here RL is the ZL, RL or ZL, whatever it is, same thing, almost same thing. You can say RL instead of RL, you can write ZL. Instead of RL, you can write ZL. Okay, instead of RL, you can write ZL. If the Z naught if the Z naught is equal to RL or the ZL, RL is equal to ZL, then what would happen? Z naught is then it would be 0, right? And the most interesting, perhaps the most obvious conclusion from the foregoing questions is there is no reflected wave if the terminating resistance is exactly equal to the characteristic impedance of the line. All energy of the incident wave is then transferred to the load, which cannot be distinguished from a line of different length and characteristic Z naught is R. Okay, so that is the thing. Okay. Some problems are there. What would happen in these cases? Let me show you. For arbitrary time functions, assuming RL a pure resistance, find the function of the incident power divided and the fraction of the incident power transmitted. So we are not calculating this. We can calculate this one. Reflection coefficient, transmission coefficient, and the power quantities. So see, so what would be the reflection coefficient? Reflection coefficient formula is ZL minus Z naught divided by ZL plus Z naught. Okay. So in this case, what would happen? So what instead of ZL, we can see if it is 0, then what would happen? Minus Z naught divided by Z naught. So it would be -1 when it is 0. Reflection coefficient. And when it is, and what would be the transmission coefficient? So for the tau 2ZL divided by ZL plus Z naught. Okay, so what would happen if the ZL is equal to 0? So 0
Sir,
Z naught. Yes. It would be 0. Like this. So nothing will transmit. Nothing will transmit here. Similarly, you can solve this one, this one, this one. you can solve this one. You see. So these are the things we have to consider. Okay, so we have just put those values instead of this, and you will get the result.
Okay, sir.
Okay, so yeah, I think you can do it by yourself. And I think I have to close here because I have to go to the campus today. Okay, so I'm closing this.
Okay, sir.
So
Okay, sir.
we have,
Are you coming, campus?
yeah, I'm going to the campus today. Will you go?
Yeah, if I come with you, inshallah.
Okay, then you can meet me. Okay, so I'm closing this one. Let me take your attendance.
Okay, sir.
Today is 21st.
Yes, 21.
21, 9/21. Interesting day.
Yes, sir.
So those are presents. Roll number 14, roll number 1,
12,
12,
18,
18, I mean
17,
17,
and 17. And 3.
Sir, 3.
3 কে আছে মনির আছে নাকি
জি স্যার, জি স্যার।
তোমরা রেজাল্ট পাইছো মনির have you
না
got
স্যার,
yet
না স্যার রেজাল্ট।
No, sir, still it's not published.
I do not know what is the problem because we have
So today, if you go to university, check for that.
check inshallah.
Okay, sir. Thank you. Goodbye.
I think it's enough so we can close the class.
You can
Allah.
close the class. Okay, sir.
Allah Hafiz, sir.
So inshallah tomorrow we'll have a class.
Okay, sir. Inshallah.
Allah Hafiz, sir.